So this is the big result of the chapter, the generalized eigendecomposition, or decomposition in terms of generalized eigenvectors. And so right now we're just going to be doing it for a complex vector space. So we're going to take some operator t, and suppose we've got the distinct eigenvalues of t, call them lambda 1 through lambda m. Then it turns out that V has a direct sum decomposition in terms of the generalized eigenspaces corresponding to each of these eigenvalues. And each of these generalized eigenspaces is invariant under T. And T minus lambda I is nilpotent on G lambda. So in other words, if we consider it as the operator restricted to just the generalized eigenspace G lambda, you have a nilpotent operator on that subspace. Okay. So we're going to prove B and C right now. We'll come back to A in a bit. So let's start with C and do everything backwards. So in fact, C is immediate from the definition of G lambda. If you go back and look at the definition of G lambda, basically it says that G lambda is the space such that T minus lambda I is nilpotent on it. I mean, you can interpret it that way. So that one falls right out from the definition. Now for B, since we have that G lambda is the null space of T minus lambda I raised to the dimension of V. Now, if you just focus on this part right here, that's a polynomial in T, right? So we have, T and then some scalar matrix, and then it's raised to some power, so you can imagine foiling it all out. What do you get? You get a polynomial in T. Okay, so the null space of a polynomial of T is invariant by the previous lemma. So 820, using the null space part, we don't need the range part. Okay. And so we'll come back and we'll prove part A. Sorry, yeah, we'll prove A in part 2. Okay, so for now, I guess we get half a box. There we go. But then I do want to point out a cheap corollary. So corollary 823, which is actually useful. And if you've taken like differential equations, like definitely 244, I think also 242, then you've actually secretly used this one probably at some point near the end of the course. And that is that if you're allowed to use complex numbers, and then in that differential equations course, it was probably in terms of matrices instead of operators, but still, you might have used the fact that V has a basis of generalized eigenvectors. So for solving systems of linear differential equations, it's often useful to resort to this particular basis. So for the proof from 821a, the part that we haven't proved yet, we have that V decomposes into a direct sum of generalized eigenspaces, right? And so then for each one of these, you can find a basis. So choose a basis for each G lambda, and then combining these, you get a basis for all of V by 813. And if you don't remember 813, it's the one that says that generalized eigenvectors for distinct eigenvalues are independent.